Alright, so we have already seen in the previous video the axiom of choice and the general idea behind it, which is just this: if we are given any collection, any non-empty collection of non-empty sets where there may be infinitely many non-empty sets, all of them are non-empty, then the axiom of choice basically says that we can choose one element from each one of them. So this is a very intuitive axiom, something that we feel should be true. But the problem is that sometimes using this axiom we can prove some things which are highly counterintuitive. But despite this, most mathematicians agree that this axiom should be considered as a legitimate axiom in set theory. Now, today we are going to see how this axiom can be used to prove something which otherwise will prove very difficult to prove. So let's see this lemma. So here we are going to see one application of the axiom of choice. So in this lemma we are given a set E, which is a non-empty subset of the set of all real numbers, such that the supremum of E is a real number. It's less than infinity. In other words, E is bounded from above. That is, there is a real number that no element of E can exceed. That is, all the elements of E are less than or equal to that real number. That real number is an upper bound for E. If this happens, then there exists a sequence an, all of whose elements, all of whose terms, all the an's are coming from E. Such a sequence is also called a sequence in E, such that the limit of that sequence is this supremum. Okay, so we have to prove it. So let's see the proof. For each positive integer n, we define the set Xn to be the set of all elements X in E, such that supremum of E minus 1 over n is less than or equal to X and X is less than or equal to the supremum of E. Well, since X is coming from E, this inequality that X is less than or equal to the supremum is always true for all elements X in E. The other inequality, however, need not be true. So here we are looking at a subset Xn of E consisting of those X for which the first inequality is true. Okay, so now the first observation about this sets Xn is this: for any n supremum of E minus 1 over n is not an upper bound for E. This minus 1 over n is not an upper bound for E. But why is that so? That's because no matter what our n is, large or small, 1 over n is a positive rational number, a positive real number. So subtracting that from supremum of E makes this strictly less than supremum of E. But supremum of E by definition is the least upper bound. It's the smallest possible upper bound for E. So this even smaller number, supremum of E minus 1 over n, cannot be an upper bound because it is smaller than the smallest. So let's write that reason. Since is the least upper bound for of E, for E same thing. Okay, so that means this number is not an upper bound for E. What does that mean? It means that all the elements of E cannot be less than or equal to this number, because otherwise it will be an upper bound, which means that at least one element in E will exceed this number to show that it's not an upper bound. So there exists at least one element, let's just call that also X, in E, such that supremum of E minus 1 over n is less than X. Existence of such an X proves that this is not an upper bound for E. But then since X is after all coming from E, X is less than or equal to supremum of E, because this is an upper bound for E. And this inequality of course is more relaxed than this one, but we can write it because this strict one implies this one, but not necessarily the other way. So we now have this, which means what? It means that this X belongs to Xn. This implies X, oh okay, yeah, instead of choosing, should I choose Xn here itself, or should I just go like this? Let me just write whatever comes next and then we will see. This implies X belongs to Xn. Thus, Xn is a non-empty set for each positive integer n. So that means we are now looking at a collection of non-empty sets. So by the axiom of choice, we can choose one element from each one of them. That one element need not be this X, of course. That's what I was thinking. I got a little confused that this X itself should be that choice. Not necessarily. So, by the axiom of choice, there exists, well, the axiom of choice says what? That there exists a tuple like this, right? X alpha where alpha varies over the index set such that this x alpha is coming from the set x alpha. What is our index set now? What type of collection are we looking at right now? We are now looking at a collection that is indexed by positive natural numbers, positive integers. So this is our index set, the set of all positive integers. This is our I. And the tuple that this axiom of choice guarantees will exist is actually a sequence whose terms are indexed by positive integers, a1, a2 and so on. So we directly write just that there exists a sequence an. If you want, you can write n belonging to this, but let's just use the more standard notation. This also indicates that same fact that n varies over all the positive integers. So there exists a sequence such that an belongs to xn for all positive integers n. Since xn, each xn is after all a subset of E, so each an also is an element in E. Now since an belongs to xn, so an will satisfy those inequalities, and that has consequence. This is less than or equal to an, which is less than or equal to supremum of E. Now looking at these inequalities, what is it that comes to our minds? What is it that we should naturally do next? Take limits and note that we are actually looking at three sequences. One of those sequences has its terms on this side, and we of course have the sequence an whose terms appear in the middle, and then we also have another sequence whose terms are constantly supremum of E. Now by the familiar limit laws, what is the limit of this sequence whose term is supremum of E minus 1 over n? 1 over n approaches 0, so the limit is supremum of E. And the constant sequence, that is this one, its limit is also supremum of E. It's equal to that constant. So it's a place where we can apply the squeeze test, which if you recall, it was like this. Say you are looking at, do not confuse this an with that an, okay, it's general. You are looking at three sequences of real numbers whose terms satisfy such inequalities, and it's given that this sequence and this sequence, they both converge to the same limit. then the squeeze test asserts that the middle one also converges to that limit, is also convergent and has that same value as its limit. So it's that one we are going to use here. So let's write the things first. Since limit of supremum of E minus 1 over n is equal to supremum of E, which is equal to the limit of this constant sequence, it follows from the squeeze test that this limit also exists and is equal to that supremum of E. So that's how we have completed the proof of this lemma. So you can see that we have used the axiom of choice here in an, I should not perhaps say essential way, but this is a very, a place where axiom of choice is, it's very natural to want to use the axiom of choice. Do you see how we are in fact needing the axiom of choice? If you do not want to use the axiom of choice here, it's not really clear how one can choose the terms an of this sequence. Why? Because do you recall that a sequence actually itself is a function? This itself is a function. What type of function is it? Let's just see that aspect a little. The sequence is in fact a function from the set of all positive integers into the set of real numbers such that f of n is an. So when we say sequence, although informally we are just looking at an ordered list of things, but formally it's a function, and a function needs to be well defined. So for every input n from here, the output should be unique and should be well defined, means it should be uniquely determined. However, since we are choosing an from xn arbitrarily, and there are infinitely many xn, so it's not clear how what rule one is using to make that choice. That's why we need the axiom of choice, which guarantees that at least such a function exists. At least there is a tuple, or in this case a sequence. Okay, so that's how we have the proof. Now, if someone imposes some extra conditions on E, then one can get the same conclusion without using the axiom of choice. And that is the next remark. For example, the remark is this. If one takes, say, E to be closed, we will see what these things are when we get to that part where we will need topology. Yeah. in many cases one can get the same conclusion of the above lemma without using the axiom of choice. If one really does not want to use the axiom of choice, then some extra restrictions on the situation will help. For instance, if E is closed and the definition of a closed set we will come across here. So we are still somewhat far away from these things. That means it's in the second volume. Then one can define the sequence AN. We have used axiom of choice to say that we have a sequence, at least one sequence. But now, because of closedness of E, we need not invoke the axiom of choice. And we can in fact define the sequence by a formula. That's what I was saying there, back there, right? That we don't know how exactly we are making the choices AN, but now we can. Such that AN is in fact the infimum of Xn. If you go back to the definition of these sets Xn, you will see that they are bounded from below as well, the sets Xn. So their infima exist since, so this is where closedness of E plays a role. Since E is closed, we have all the ANs in E. How that happens and why that happens and how that thing is related to closedness, we are yet to see. But in some such situation with some extra restriction, we can get the same conclusion without using the axiom of choice. But note that we are using an extra condition that E is closed. However, in general also it's true, but for that we need the axiom of choice. At least if we want to prove it so simply. Now, the axiom of choice, the way we have stated it, there are other ways of stating the same thing. In other words, there are other formulations of that same axiom, which we will see in the exercises. Now, here is another formulation, which has been given as a proposition. This is proposition 847. So it's going to be a statement that is equivalent to the axiom of choice. We will of course have to prove that equivalence, which we will do in one of the exercises. So let's now see the statement. Let X and Y be sets. Let Px, Y be a property pertaining to an element x in x and an element y in y, such that for each x in x there exists at least one y in y for which the property is true. This kind of property, depending on two objects, for this you can go back to the axiom of replacement from set theory. We left it way behind in the third chapter, but if you go there, you will see that there we have axiom of replacement among one of the axioms. So there you will see this kind of thing. So what we are saying here is that we have two sets x and y, and there is a statement, something that is either true or false, but the statement depends on an element x coming from x and an element y coming from y. So we can of course change these x and y independent of each other, of course. So for any such choice of x and y, x from x and y from y, this p may be true, it may be false. In that sense, it pertains to these elements. But there is a condition. The condition is that for each x in x, there exists at least one y in y for which this is true. So we will never come across an element x in x for which there is no y such that this statement is true. That won't happen. Okay, at least one y you will get for each x. Now what? Now the claim is this, the assertion is this, then there exists a function f from x into y such that p of x comma f of x is true for all x coming from capital X. So what the author says is that this is a formulation of the axiom of choice, which means that if we assume the axiom of choice to be true, then this can be proved. In fact, in that format it's given. So we are asserting this thing and we are going to prove this by using the axiom of choice. But since it's a reformulation of the axiom of choice, the converse is also true. That is, if you take this to be true, then you can prove the axiom of choice as a consequence. So in that sense, they are equivalent. And so this is another reformulation of the axiom of choice. We will see other reformulations also in the exercises. And for the proof, we will have to wait till we solve exercise That is the first exercise of this section. You can perhaps at least understand how this statement is related to the axiom of choice. The proof, of course, we won't do today, but let's at least see, maybe vaguely, how this is related to the axiom of choice. So what is being said is that for each x in x, there is at least one y in y for which p of x comma y is true. So you can think of the situation like this. Because we have seen this part, let me just clean this, and here I can draw my diagram. The situation is like this. This is our x, this is our y. We have, just for the sake of our understanding, let's just take 2 or 3 elements in x. There may be others also. For this x1, let's imagine a set of y's. Yx, let me use x as, this is not power, x is superscript. It indicates the fact that this element y1x depends on x, well, it is x1, y2 x1, and so on. These elements are precisely those elements for which p of x1 comma this is true. Then there is, say, another set of some y values which come because of x2, and so on. For x3 you will get some other y values, y1 x3, y2 x3. So the given condition asserts that these sets are all non-empty. Naturally, because that's what we are saying here, that for each x here, there is at least one such y for which p of that x comma that y is true, that statement is true. So we have a collection of non-empty sets. So by the axiom of choice, you can choose one from each one of them, and that choice will give you this function, so that this is true. So we are almost looking at the proof of this, but we will of course do it in the next video. So that's just it. This section in fact ends here. After this, the exercises start. So from the next video we'll start solving the exercises, and our next upload is this coming Tuesday, right? On Tuesday, let's go back to calculus. So with that, I end our video tonight. So see you on Tuesday with calculus. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.